Section 3.2b, logarithmic functions and their graphs. We're going to look at natural logarithmic functions. It's a specific type of logarithm with a certain base that we talked about before in terms of the natural base. Don't forget that a logarithm is an exponent, and as we go through really all this entire unit, keep reminding yourself a logarithm is an exponent. That'll help out a lot. So, what is the natural logarithmic function? Well, we know f of x is equal to e raised to the x power. That's the natural base, but it's also a one-to-one function, so therefore it has an inverse, and we call the inverse the natural log function, which is read or written as ln of x and read the natural log of x. So when you do this, you got to be careful because natural logarithmic functions, we write it as ln of x, but it's still a logarithm, and the logarithm is the log with base e. So we still have the same stipulations: x must be greater than 0, and y is equal to natural log of x if and only if x is equal to e raised to the y power. So make sure that you understand natural log of x is the same thing as log base e of x. So we're not going to write it as log base e of x. It's written as natural log of x, but it's still a logarithm. It's just with that base of e, which is that irrational number. Because the functions are inverses, their graphs are symmetric to the line y equals x. So you can see that I graphed f of x equals e raised to the x, so that's the exponential function. And then I went ahead and graphed the inverse of that, which is the natural log of x. And that's log, remember, log base e of x. And so you can see that they are symmetric to the line y equals x. They do represent inverses. So we have two very specific type of logarithms. We have log base 10, which is your common log, and log base e, which is your natural log. Those are the two buttons on your calculator in terms of the bases. You have base 10 and base e. And base e, once again, is the natural log. Alright, now we're going to evaluate a couple of these using the calculator. So we're going to use f of x equals the natural log of x. We're going to round to the nearest thousandth. So if x is equal to 3, f of 3 is equal to the natural log of 3. So press the natural log in your calculator and you can see we get 1.0986. We'll round that to 3 places. So the natural log of 3 is approximately 1.099. Now you can also see below that I used the inverse, so I said e raised to that value, 1.0986, should be equal to that input value of the natural log, which is 3. So once again, just kind of checking to make sure each of those are correct. So on the next one, we have natural log of 0.8. And so when we plug that in, we get that the natural log of 0.8 is approximately negative 0.223, once again showing that if you use its inverse, e raised to that power, you get back 0.8. And then the last one, we have f of negative 5, so that's the natural log of negative 5. And hopefully you already know before you even plug it in that it does not exist, because that x value right there is greater than, or is not greater than 0, it's less than 0. So therefore, based on the definition, this one does not exist. So those are just 3 examples of plugging them into the calculator, and once again also checking to make sure that we are doing them correct by using its inverse. Properties of logarithms also apply to natural logarithms. Once again, natural logarithms are still logarithms, just log base e. So the 4 properties we had before are the same 4 properties we have now. It's just now instead of using log base a, we're now using natural log or log base e. So you can see natural log of 1 is equal to 0, natural log of e is equal to 1, natural log of e raised to the x is equal to x, and e raised to the natural log of x is equal to x. That third one is your inverse property, the one that once again we will probably be using most frequently. And then we also have the one-to-one function where you have the natural log of x is equal to the natural log of y. Then it must be true that x is equal to y. So same 4 properties. Let's go ahead and simplify a couple of these now looking at our natural logs. But don't forget, natural log is log base e. So even if you need to write it, for example, on 2a, if you say e, natural log of 9, but if you write it as log base e of 9, you can see you have an exponential raised to log base e. So the same bases there, they cancel out, and you're just equal to 9. So I don't mind you taking natural log and writing it as log base e until you become familiar with it especially. So natural log of 1 over e. So this would be log base e, 1 divided by e. Well, we can rewrite that. So log base e of e to the negative 1, and then you can see that that's the inverse property, and they cancel each other out to give you negative 1. So that would be the inverse property that's being used on that one. And the same thing on this first one. This is the inverse property as well. On 2c, 3 natural log of e. So 3, once again, just to get familiar, log base e of e, and that's to the first, so those cancel. And it's 3 times 1, which is equal to 3. And then on d, same idea, natural log of e raised to the 0, or log base e of e to the 0, cancels out and just gives you 0. So one of the last things we're going to talk about is the domain of a logarithmic function, which we have talked about, because remember that for x greater than 0 and a greater than 0 and a not equal to 1, y equals log base a of x, if and only if x is equal to a raised to the y. So this value of x must be greater than 0. And that has to do with its inverse function, that having to be greater than 0 as well. So when you go to rewrite it as a logarithm, it still has to apply. So to find the domain, what we want to look at is we want to look at specifically that value after the logarithm and make sure that it is greater than 0. So we can take that expression and say x minus 3 must be greater than 0 and solve. And so we know that the domain must be all values that are greater than 3. So you can plug in any value that's greater than 3. You can't plug in 3 because that'll give you 0, but anything larger than that would give you a positive value. Same thing on the next one. 3 minus x must be greater than 0. Add the x to the other side, so x is less than 3, so your domain is values that are less than 3. And then on the last one, this x squared must be greater than 0. Well, when you square a number, it's always going to be greater than 0 except for what? X cannot equal 0, because if 0 squared is 0, that will not be greater than 0. So on this one, your domain is x such that x cannot equal 0. You could also write that in interval notation, and it would look like this. All values of x except for x equals 0. So that's how you find the domain of a logarithmic function. All the other stuff, remember, doesn't matter. It's just the after the logarithm, that x value has to be greater than 0. So whatever that expression is must be greater than 0. Solve for x. That will give you the domain of the function. And so once again, write your summary for this lesson as to what those important things are that you were able to take out of this, and what things we need to definitely know as we move forward.